Hi, everyone. Thank you so much for coming to my talk. And thank you so much for the organizers for letting me give this opportunity to share my research. My name is Eli Draizen, and I'm currently a postdoc with Andre Shally at UC San Francisco. But I'm going to be talking today about my PhD work I did in Phil Bourne's lab at the University of Virginia. My talk is titled, "Is this yet another multiverse talk? Exploring murky regions of the protein multiverse with ancestral fragments and deep generative models." Before we begin, we have to understand, what is the protein universe? You might have seen some really new, exciting representations of the protein universe that came out a couple of months ago from the FoldSeq team, who identified 2.3 million clusters in the AlphaFold database, as well as the Schwade-Perea team, who annotated all sequences in uniprot clusters with functional brightness. But what exactly is in this protein universe? The current definition of the protein universe is that it contains all possible proteins that ever exist. But what does this actually entail? These databases only include modern day extant proteins. But what about ancestral reconstructions of proteins or ancestral fragments? Does this set contain proteins that don't even fold into actual structures? And is this space infinite? So we have to understand what this space actually represents. And one way to do this is understanding how the universe is organized by understanding the different clusters or understand which regions have more density than other regions. And if we do that, we'll be able to learn more about protein interactions, drug targets, and what I'm especially interested in is their interrelationships. How can we find exceedingly remote relationships between different proteins? As I alluded to in my title of this talk, is this a multiverse? We have so many different representations of the protein structure universe. We have to understand what we're actually looking at. It's probably not a multiverse. I was just talking, it was a funny title, but we do have multiple representations of this protein structure universe. So we should look at all the representations that we have and understand their similarities and differences and their strengths and weaknesses. So going back from the beginning, we have some early representations of the protein universe, such as from Homan Sander in 1996 and Sung-Hao Kim in 2005, where they take a pairwise similarity matrix of different protein structures and create this latent space to see what these proteins occupy. We have different examples all the way for the past 20 years. But another great example of the protein universe is from CAF, which organized protein domains in a hierarchical representation based on secondary structure. And then we have up to today, where we have UniProt 3D, where they clustered all the UniProt sequences in different clusters and colored it by functional brightness. While all those have different questions they're trying to answer, they do have one similar goal, is they're trying to organize the protein universe such that proteins with similar structures and functions are nearby so we can learn more about them. As you can see, there were two different representations of how people represent the protein universe. One way is through an embedding space here on the left, where a neural network is trained, and the embeddings from that neural network are plotted in some dimensionality reduction to see what we see on the screen. In this case, it's from a protein language model from the evolutionary scale models, and this is representing lots of metagenomic sequences. However, the questions they're trying to answer are different than other protein universe questions because these are trying to generate new proteins and finding out what is novel and what is not. So it's colored by the nearest neighbor in the protein data bank. And the distance itself is implied in the position of the embedding. Another representation is the network representation, where you have each node is a different protein and they're connected if there is some similarity between them, which can range from different scales. In this example, it's using sequence comparisons using e-values from MMSeqs, but it could also be from structural alignments. And this representation is also colored by the percent of functional annotations of the closest homologue. So these two representations, while they're showing many of the same proteins, they have different end goals. One's functional and one is novel proteins. Another aspect to be thinking about when looking at the protein structure universe is what scale are we referring to? Both of those two examples look at the full protein sequence or the full chain, but other representations that I've talked about previously look at the individual domain, such as the databases of CATH, SCOPE, and ECOD. This asks the question, what is the evolutionary unit of the protein structure universe that we should be looking at? Another aspect we could look at is the ancestral fragments. So even subdomain fragments. How can these different domain fragments combine to create all the domains that we see today? That is an even smaller level, and it could be looking at a completely different protein structure universe. One interesting thing that you can do with these protein structure universes is cluster them to see if there's any evolutionary information. So for example, when we look at the protein structure universe, we're looking at all modern day proteins. But can we go back in time and see maybe the clustered nodes are actually represented by ancestral reconstructions? Or can we go all the way back in time before the last universal common ancestor to see if maybe it's ancestral fragments at the very base of this tree? This is a really interesting hypothesis, but unfortunately, we do not have enough evidence or information to actually construct something like this. However, we can use clustering to do another approach to look at the protein structure universe by organizing the protein structures by secondary structure, which is what they do in the CAF hierarchy. So starting with the clusters that they found in the protein universe, they cluster that, and that's what is typically called homologous superfamilies, where the domains share greater than 20% sequence identity. You also go deeper in this tree and organize them by the topology, which is the patterns of connectivities of the secondary structures. You go even deeper to look at the architecture, which is the relative positions and orientations of those secondary structures in 3D space. And finally, you can look at the class, which is just the predominant secondary structure elements found in the protein, such as all alpha, all beta, or alpha/beta. This organization of the protein structure universe works really well for many proteins, but there's a few edge cases that makes it really hard to determine a protein structure, function, and evolutionary relationships. For example, what if a protein can occupy two bins at once? It's not a discrete clustering, as is the case with the small beta barrels, what we've been studying in our lab, because they represent architectural similarity despite topological variability. As you can see, these protein structures look very similar. You can superimpose them, and they have the same secondary structures in similar locations, but the loops between them are different. And they're classified in completely different CAF hierarchies, yet they share many of the same functions. So they both bind DNA and RNA, and they also have bind other proteins at the same edge strands. And really the only difference is if you look at the secondary structures laid out in a one-dimensional space or 2 dimensions, you can see it's only just an alpha helix that's been shifted down by 3 beta strands. It's remarkable how much sequence variation this family can tolerate while still retaining the same overall structure or architecture. Because of this phenomenon, we think there should be a new entity in the CAF hierarchy in between architecture and topology that we call the fold to represent the 3D architectural similarity despite topological variability. Through manual searches of the protein databank, we found several other examples, such as the P-loop NTPases, KH domains, and several from Archaea. While this is only a few examples, we think it's actually widespread through the protein universe. So just to summarize, the CAF database is a hierarchical classification system, which works really well, but there's some discrete clustering that makes it difficult to find proteins that occupy multiple bins. So we propose to look at the protein structures through the fold lens, where we can put in a new entity between architecture and topology to represent the architectural similarity despite topological variability. We also think the fold model supports themes or ancestral fragments because we can look at the Rossmann and the P-loop NTPases because they share a similar fold of the 3 beta strands with an alpha helix, but the loops between them are different. And if you organize them in this type of universe, they'll be clustered together in a similar way. So the overall question I'm trying to ask is, can machine learning teach us how proteins were formed from smaller, potentially discontinuous fragments, and how can we find them? The overall goal or the overall model that we're trying to do is learn the probability distribution of individual CAF superfamilies. We want to be able to ask, what is the likelihood that a given domain arose from the superfamily specific model? However, this distribution is unknown, so we have to estimate it from the data. This is a generative model can learn this type of probability distribution, and it's called generative because you can also just sample from this distribution and generate a new structure entirely. However, we only are interested in protein structures that already exist. In order to determine this probability distribution, we're using variational autoencoders, where we first take a protein domain from a given CAF superfamily, turn it into a 3D image by voxelating it, and then attaching different biophysical properties to each atom, and then putting the atoms that intersect with different voxels with those features. Once we have that three-dimensional image, we can put it through a sparse encoder 3D CNN, which compresses the image down into a latent space where it learns the mean and variance of a normal distribution. And from that normal distribution, we can sample from that and then reconstruct what the domain might look like in terms of the model. So we have this new predicted structure with a new volume and predicted features. And we train it using the evidence lower bound, which is the lower bound of the log likelihood function, where we first look at the reconstruction error, so the difference between the reconstructed volume and the true volume and the features that it's predicted, along with the similarity between the learned distribution and the true distribution estimated by the Kale divergence. However, that's just training for one superfamily, but we do this 20 times to learn about 20 different superfamilies. So we do this first by training one model per superfamily with different representatives from that superfamily. Then we subject all representatives from all the superfamilies to all the other superfamily models. Then we save the domain embeddings from the encoder module, which is the mean of the normal distribution, and then we can concatenate them to view them as what the embedding might look like. So to make this a little clearer, we put one domain structure through each of the superfamily variational autoencoders, get the mean of the normal distribution, which is the embedding, concatenate all of them, and then use UMAP to reduce the dimensionality into 2 so we can visualize it on the screen. The first thing you can notice is that it looks like the Starship Voyager from Star Trek, where the mostly beta proteins are on the bottom nacelle, the mostly alpha are on the top nacelle, and the alpha/beta are in the middle, which is an interesting finding that there is some gradient based on secondary structure in this UMAP version of the protein universe. But it is just UMAP representation, so we don't know if this is actually correct. So we also do a clustering representation of the protein universe. So in order to cluster what we have right now is we do the same thing what we did before, where we train one model per superfamily, and then we subject superfamily representatives to all the other superfamily models. And then instead of saving the embedding, we save the elbows likelihood that represents the likelihood that one domain arose from a given superfamily. And then we use that to weight these edges of the fully connected bipartite graph, which is the domains on the left side and the superfamilies on the right. Then we can cluster this fully connected bipartite graph using stochastic block models, which are a probabilistic graphical model that can detect hierarchical mixed membership communities in fully connected bipartite graphs with variable edge weights. This is important because some of these proteins are going to span multiple communities or different clusters, such as the OB and the SH3. So when we do this, we get a new representation of the protein structure universe. The first thing we can see is that there's a lot of intermixing between different superfamilies. So this should be, if the cath was correct, all the same color would be in the same circle here, but we can see there's a lot of intermixing. But that's actually interesting because we see the small beta barrels, the OB and the SH3, clustering together in the same community. Because of this intermixing, we think there's more similarity at the subdomain level rather than global structure similarity. Another interesting thing we found with this clustering of communities is that proteins with similar electrostatics cluster together in the same community, whereas in cath, there's no clear pattern. One issue with looking at the protein structure universe is that there's no ground truth. We don't know what the true representation of the universe should be. So the best way to do it is to compare against cath. However, if we're trying to compare clusters, we were saying that if the clusters are least similar, or the clustering metrics are least similar to cath, it's more likely the Erfold model might be correct. While doing this, we also compare different protein structure and sequence similarity algorithms and cluster that using stochastic block models to try to reconstruct cath as well. And to measure these similarities, we use the silhouette score, the overlap, homogeneity, and completeness. So when we do that, the first thing you can notice is that Deep Erfold does not do as well as the others. It's still better than random, which is a good sanity check, but it's still learning something completely different. So it might not be the hierarchical clustering of cath might not be the correct way to view fold space. Since we have a different representation of the proteins, it includes the van der Waals representation of each atom that's been voxelized with biophysical properties, compared to the other ones which just use sequence or 3D atomic positions. But because of this, we think our model is learning something beyond simple structure and geometric similarity, but towards the realm of structural and functional properties. As I said before, in our clustering, we found multiple superfamilies in one community, and we think that they're most similar at the subdomain level rather than the global domain level. So we want to be able to identify these subdomain fragments by finding relevant regions from the neural network. We do this using layer-wise relevance propagation, where you can first input a protein domain through the model, and then stop at the latent space, which represents the normal distribution. And then you can do a backwards pass through the entire model, trying to identify which neurons were activated at each step or each layer. You can map that all the way back into the input voxel space and map that back to the atom space as well. So we're trying to do that with the EarFold as well. We want to understand if each variational autoencoder model can learn biophysically important features that might be functionally relevant for each superfamily. So we do this first by subjecting domain representatives from the Rossmann through a learned Rossmann model. You can see here that it identifies the phosphate binding loop as most important. This is the loop that classifies this family as one of its functional roles. Then we also run the Rossmann through the p-loop model as well. And you can see it also pulls up the p-loop as the most relevant region. And same thing, we run the p-loop domain through the learned Rossmann model, and it also identifies the p-loop as the most important region, and same with p-loop through the p-loop model. Because of this, it doesn't matter which model you put it through, so anything with the same EarFold will classify things in the same way. In doing this, we were able to extract all the different relevant residues from an all-by-all model comparison, so we can get a core set of what these EarFolds might be in terms of these relevant structures. And that's going to be another view of the protein structure universe, where you just have these core fragments at the base level. So in conclusion, there are many different representations of the protein universe. While they all deal with similar protein inputs, they have different goals, such as they're looking for functional information, evolutionary information. Some might be looking at different clustering stringencies by different cutoffs. They might be looking at different scales, such as the full chain or single domain. So you have to understand what you're looking at to understand the protein universe. And in this project, we identified two new views of the protein structure universe with variational autoencoders. The first one I showed you was from the embedding space, which takes the encoder output from the variational autoencoder, which is the mean of the normal distribution. Also showed a network representation where we clustered likelihoods from an all domain by all superfamily approach using stochastic block models. I also showed a first glimpse of what a pre-Luca protein structure universe might look like based on ancestral fragments that identified via layer-wise relevance propagation. But overall, we think our view of the protein structure universe will allow for the EarFold model of protein relationships to allow for architectural similarity despite topological variability. I'd like to thank everyone in my lab who's helped me out with this project, especially my advisors, Phil Bourne and Kem Mura, as well as Stella Vretnik and Zhang Zhao, who are staff scientists in the group. Thank you so much. Do you have any questions?